This is part 5 of circuit design, and I will conclude part 5 with the analysis of driver circuits, and then will move on to input. The processor here is a digital machine. Therefore, it only has two states, on and off. And you have to read the data sheet in order to know what the on voltage, what the typical on voltage is, and what the typical off voltage is, and what kind of current it can provide. Also, you can read a data sheet to find out about how much current is needed to operate the transistor in the saturation region. But what I wanted you to be aware of is this. The part of the circuit that is connected to the microcontroller is pretty standard. You connect it here through a value. A typical value might be 1 kilo ohm, and you're done. Usually 1 kilo ohm with a 5-volt source is more than enough base current to push this transistor into saturation. But once again, you may have to read the data sheet because there are a wide range of transistors to choose from. So you may have to use the data sheet, but you can begin with 1 kilo ohm. If 1 kilo ohm doesn't work, then you can use 100 ohms. So you can do experiments to determine what will be the right resistor that you need. Or you can do precise calculations by using the data sheet. So now the analysis becomes very direct. If you, for example, assume for all practical purposes that the voltage drop from the collector point of the transistor to the emitter point of the transistor is 0.5 volts. And you also assume that the current going into the collector will be very close to or equal to current going into the emitter, then you basically have a series circuit. The only difference is that you have to deal with the 0.45 volts from the collector to the emitter in your calculations. So you can come up with a formula called V total is equal to the voltage from the collector to the emitter plus, you can say V load 1 plus V load 2 plus V load 3. Now these loads could be a lamp, or it could be a resistor, or it can be a LED, but these voltages will add up to the total voltages. So I can use an example like this. Imagine that I have a power supply and I connect a resistor, another resistor, and another resistor here, and then at the bottom I join this to the negative, I basically have this formula. V total is equal to V1 plus V2 plus V3 plus the voltage from the collector emitter, we're going to assume to be 0.5 volts. Sometimes it's a little bigger, sometimes it's a little smaller, but you can get that information from the data sheet. And these other values will be determined by your design. So this becomes your new load circuit. The only difference between this load circuit, the only difference between this load circuit and the load circuit that you studied at the beginning is that now you have added another component in the series network, which is the transistor. But the analysis is still the same. Let's do a simple example. Let's, for example, you want to drive a lamp. So very simply, you would put the lamp in the path of the load circuit. And let's say this was a 3-volt lamp operating at 150 milliamps. And let's say you're going to use the same power supply as you used before, 5 volts, 1 amp maximum. Now, of course, this power supply is also being used for other circuits. So you have to be sure that your power supply has enough current for all of the loads that you connect. But for now, we're just going to assume that this one power supply is being used for this lamp. Now we know we cannot connect this directly because even if you use the 0.5 volts, the 0.5 volts plus the 3 volts will not equal to the 5 volts. Therefore, we must insert a resistor for the other voltage. So we have now a V total, we have a V1, we have a V2, and we have a V from the collector to the emitter. We have the formula, V total is equal to V from the collector to the emitter plus, I'll go this way, V2 plus V1. If we substitute these values with numbers, we have 5 volts is equal to 0.5 volts plus the voltage that we want for the lamp, which is 3 volts, which leaves us with an unknown voltage for the resistor. And we know after we do the math for this, the V1 will be equal to approximately 1.5 volts. That will be the voltage for our resistor. Now, since we want to operate the lamp, we must force a current of 150 milliamps around this series circuit. Therefore, our calculations must make this series circuit 150 milliamps. This is what we want. So if 150 milliamps flows through the lamp, then we need to use this resistor to make sure that we get 150 milliamps. So if we assume that the current through this resistor will be 150 milliamps, then now we have enough information to calculate the value of this resistor to make it true. 1.5 volts divided by 150 milliamperes using our calculator. Give us 10 ohms. So we can use a 10 ohm resistor to help control the current in this series driver circuit. Remember, over here, this is being taken care of. We have pushed the transistor into the saturation region, which means the base no longer controls the current directly, and we can just push as much current as we need through the collector, because now the transistor has collapsed, and now the current is being controlled by the circuit over here. As long as we do not exceed or go above the maximum collector current that's allowed by the transistor, then we can operate a wide variety of load circuits. And the operation of this circuit will be controlled by the microcontroller, and the program in the microcontroller will decide when this will be 5 volts and when this will be 0 volts. Or we can say when it will be on and when it will be off. That concludes my tutorial on driver circuits. Quick summary. In the beginning, we talked about loads, and we said there are various types of loads, and we understand how they work and what information you need. We proceeded to talk about load circuits when the voltage is equal to the component or when the voltage is more than the component. After that, we said we can use a microcontroller to drive the load, and the program will be used to turn the load on and off. Then we realized that sometimes the actual component that we want to drive exceeds the amount of current that can be supplied by the microcontroller. Therefore, we must use another component to allow current to flow directly to the load without having to pass through the microcontroller. And this will be controlled by the microcontroller, which only needs a smaller amount of current. We summarize this by talking about the principle of multiple loads on a single power supply, and the microcontroller will control when the other networks will be on or off. So we have a parallel circuit where one network in the parallel circuit is responsible for controlling when the other networks will be operating. Lastly, I wanted to show you in detail how you would do the analysis and design of a load circuit through a driver component such as the transistor. Thank you.